having wrapped up an investigation into different types of chemical bonds and so different types of chemical compounds, we're going to dive into naming and formula writing. And so we're going to start by looking at covalent and ionic compounds. There's a different set of rules for naming each of those things, so it's really important that you can categorize. So what we're going to do is start with covalents because they're the easiest to do. And so here's the deal with covalent compounds as compared to ionic. If you have an ionic compound like magnesium chloride, the magnesium has a 2+ charge, the chloride has a 1- charge. The only way that compound can form is if there's 1 magnesium and 2 chlorides. So when we name that magnesium chloride, we make no indication that there's 2 Cls. We make no indication that there's 1 Mg because the charges dictate that that's the only way to form that. But if you're looking at compounds made out of, say, carbon and oxygen, 2 simple versions of that are carbon monoxide and carbon dioxide. The carbon and oxygen, because when we're sharing electrons, there's so much variability in sharing. We have single bonds, we have double bonds, we have triple bonds. And so multiple or nonmetals can combine in multiple ways, and just saying carbon oxide doesn't help us sort out those 2 things. Once we get into talking about carbon compounds of carbon and hydrogen, there are hundreds of variations on that. An entire branch of chemistry called organic chemistry simply looks at the compounds made out of different variations of carbon and hydrogen chains, and then some other side chains there. And so we need a way to differentiate these compounds one from the other, because again, saying carbon hydride does not really sort that out for us. And so with covalent compounds, we use a set of prefixes. So you should jot these down somewhere. These are things you're expected to have committed to memory, but really you kind of know this stuff already. Like, it's not surprising that the prefix for 2 is di, 3 is tri. 4 might be one that you haven't seen before, so we're going to use tetra there instead of like the QU prefix that we'd use on like a quartet. So 4 in chemistry is tetra, but penta, hexa, hepta, 5, 6, 7, octa, as in octopus, right? So we've seen these other prefixes, so really you just have to make sure that you know that 4 is tetra. But you should write those down, commit them to memory, because you're going to need to be able to use them. So there's 2 ways that we're going to come at each of these. Either you're going to be given a name and you have to write a formula, or you're going to be given a formula and have to write a name. So if you're given a formula and you need to convert it to a name, then you're just going to look at the subscripts and convert those subscripts to prefixes. So we'll put a prefix and then the first element name, and then we'll do a prefix and the second element name, and then we'll always change that second element to IDE on the ending. The little asterisk there is to let you know that the mono prefix for 1 of something is never put on the first element. If you only have 1 of the second element, then we do use the mono prefix. So take, for instance, PBr3. We're going to name the first element. It is phosphorus. There's only 1, so we don't say monophosphorus, we just say phosphorus. Had there been 2 phosphoruses, then we would refer to that as diphosphorus. So you'd use any other prefix but mono. Then there are 3 bromines. We're going to change that to bromide, and we're going to get that prefix tribromide. And it's that simple. The subscripts become prefixes. On the other way around, if you're given names and asked to write formulas, you're going to write the first element and convert your prefix to a subscript. You're going to write your second element and convert the prefix to a subscript. So here we have dinitrogen dioxide. So your first element, there are 2 of them. It's nitrogen, so we go N2, dioxide, and so 2 oxygens, we go O2. And that really is the setup. Covalent compounds are the easiest ones to name. They're the easiest ones to write formulas for because there's nothing to figure out. The subscripts become prefixes, the prefixes become subscripts. So take a second, look at the name on your screen, pause the video, write a chemical formula. Our tetra prefix there means 4, so 4 carbons. Deca is our prefix for 10, and so decahydride. And so you should have C4H10. On your homework, you're going to have problems that go past 10. So on any quiz or test, I'm not going to expect you to know past 10. If you find a prefix you don't recognize while you're working through problems, you have the sum of human knowledge in front of you in the form of the internet. So Google the prefix and see what it means. All right, let's switch now to ionic compounds. In ionic compounds, we need to be able to balance charges. So again, there's going to be two ways we'll come at this: names to formulas, and then formulas to names. If you're given a name and you have to find a formula, well, write down the cation with the charge, write down the anion with the charge. And so if you're given the name potassium sulfide and you're asked to find a chemical formula for this, start with potassium. Potassium's in group 1A, so it always loses one electron and forms K+. Sulfide is in the oxygen group 6A, and it gains 2 electrons, and so you get S2-. We're going to crisscross the charges. We need 2 1 pluses and 1 2 minus, and so our formula there is going to be K2S. And this is stuff we've already done in our ionic chapter. If you are given a formula and asked to find a name, well, name the cation, name the anion. Every ionic compound is going to have 2 names. You don't need to worry about subscripts because the subscripts are fixed by the charges. So if we get Ca3P2, all I need to do is name the first thing and name the second thing. So the first bit is calcium. The second bit is phosphide. We change the ending to IDE. Now, these are binary ionic compounds. They're the simplest form of this, but we've kind of seen hints that there's more complex ionic compounds using what we refer to as polyatomic ions. Polyatomic ions are combinations of nonmetals covalently bonded together that have either a few more or a bit fewer electrons than you would expect them to have from their elements, and so the covalent compound carries a charge. In front of you, you see 11 polyatomic ions. These are some that you are expected in this course to commit to memory. So you should make your flashcards starting right now. You need to know these, and you need to know these quickly and be able to write formulas that involve these. There are other polyatomic ions. These are some of the most common ones, and so these are why we're going to use these. Also, it's kind of important just as a learning exercise to be able to store important information in your working memory to be able to work through over a short period of time. In this case, we're talking about the next roughly 3+ months. We're going to be using these polyatomic ions as a central feature of this course, so you need to get them committed to memory and put them in your working memory so that you can access them quickly. All right, so let's talk about names to formulas when there are polyatomic ions involved. So it's the same basic process. Write the cation, write the anion. And so if you start here with potassium sulfate, you're going to start with your potassium cation the same way we did in our last problem with potassium. It's just K+. Sulfate, then, you know just by hearing that, once you learn these, that's SO4 2-. 1 sulfur, 4 oxygens, 2 extra electrons than it should have, carries a 2- charge. For naming purposes, it's super helpful if you put these in parentheses with the charge on the outside. Treat the inside of the parentheses like it's a single element, because it is, in fact, a single particle. The sulfurs and the oxygens are covalently bonded, and they form a single particle that interacts the same way an S2- would interact in an ionic compound. Crisscross the charges the same way. I need 2 Ks, I need 1 SO4, and so I get that. Unless there's more than 1 SO4, you go ahead and drop the parentheses. So the final answer here should be K2SO4 or potassium sulfate. Let's try another one. Again, you need to name the cation, name the anion. So take a look at this one. Notice that there is no metal. You have this thing in parentheses that comes first, and when we write ionic compounds, cation always comes before anion, so that NH4 has to be our cation. If you go back and look at your list of polyatomic ions, you will see that this is NH4+, and its name is ammonium. It's a 1+ charge. Sulfide is a 2- charge. That's why we need 2 ammoniums and why we have parentheses around the NH4. As far as counting atoms, in this compound you have 2 nitrogens, 8 hydrogens, and 1 sulfur total. And then the anion here is sulfide, and so the name of that compound would be ammonium sulfide. Okay, let's talk about going formulas to names when there are transition metals. You may remember transition metals can form more than one charge. On your periodic table, you want to look just above the symbol to the element, and there will be a list of numbers separated by commas. Those are the possible cations that transition metal can form. And if you are trying to name ionic compounds with transition metals involved, we're going to use Roman numerals to differentiate what kind or what the charge is on the cation. So here's one to take a look at, FeCl2. If you look at your periodic table, you'll note that iron can form a 2+ charge or a 3+ charge, and so we'll need to designate which one we have here. First thing I want to do is just name the two elements, and then I'll figure out the Roman numerals. So I know Fe is iron, and Cl is chloride. I'm going to leave a little space for that Roman numeral, and we're going to kind of work backwards from the anion to figure out what the charge on iron is. You will always know the charge on your negative. And since you know the charge on your negative, you can figure out the charge on your positive because ionic compounds are electrically neutral. So we have FeCl2. The charge on a chloride ion is 1-. There are 2 chlorides. So the total negative charge that this compound is carrying is a 2- charge. Iron is carrying a 2+, or the iron has to carry a 2+ charge. Because there's only one iron, that has to be carrying the total 2+ charge. So the charge on each iron, there's only one this time, but if there were more than one, the Roman numeral is the charge on each iron, not the total positive charge. So we would refer to this guy as iron 2 chloride. There's a tendency for people that are learning this for the first time to want to look at that subscript on chlorine and go, oh, the 2 means there's 2 chlorides. That's not what the 2 means, and it will not always work out that way. The 2 is the charge on the iron. In this case, because the chlorides have a 1- charge, you need 2 of them to cancel out the 2+ on iron. Let's try another one. So you should write that down. You should check your periodic table to see the possible charges on Ti, and you should write down a name for this compound, pause the video, and then we'll take a look at the answer. Okay, so hopefully you took a stab at this. Ti, if you look at your periodic table, is titanium. O2 is going to be oxide. And then we're going to work over here to figure out what the charge on our titanium is. Again, separate your cation and your anions out. Charge on an oxide is 2-. There are 2 oxides, so the total negative charge is going to have to be 4-. Total positive charge is going to have to be 4+. Since the subscript on Ti is 1, that means each or the only Ti carries the full 4+ charge, and we'll put the Roman numeral 4 in there, and this would be called titanium 4 oxide. Give you one more practice. This time we're going to add a little piece to here that we have a polyatomic ion involved. So take a look at this one and see if you can figure out what the formula or what the name for this compound is going to be. Go ahead and pause the video. All right, so let's take a stab at it. Again, name the cation. Cu is copper. Name the anion. You're going to have your polyatomic ions committed to memory. You're going to see that SO4 and know that that has to be sulfate. Okay, we're going to separate our ions. Again, I'm going to go ahead and put the polyatomic in parentheses. Charge on a sulfate, 2-. Again, this is just something you have to commit to memory. There's only one sulfate, not 4. They would have to be parentheses and a number on the outside of the parentheses if there's more than one sulfate. So the total negative charge is 2-. Total positive charge is 2+, but this time we have 2 coppers. So each copper has to be carrying a 1+ charge in order for the total positive charge to be 2+. So we're going to refer to this one as copper 1 sulfate. We flip this around and start talking about how are we going to do formulas to names with transition metals. Well, this is actually easier because, that was names to formulas. We're not quite there yet. Looks like I have one more practice for you on formulas to names because they are a little trickier. So here's one. Take a stab at it, see if you can get the answer. Okay, PT is platinum. NO2 is nitrite. I'm going to separate out our cations and anions. Nitrite carries a 1- charge. There are 4 of them, so the total negative charge is 4-. Total positive charge has to be 4+. There's only 1 platinum, so it has to be carrying that 4+ charge. And so platinum 4 nitrite. Okay, now let's do the names to formulas, and these are actually easier because you don't have to look at the periodic table to figure out what the charge is like you do with a representative element. When you have a transition metal involved or an element that has more than one valence state, the Roman numeral tells you the charge on the compound. And so we look at this one. We're going to write the cation and its charge. We're going to write the anion and its charge. Nickel 3 means we have a nickel 3+. You don't have to check up on anything other than the chemical symbol for nickel if you don't know it. Sulfide is 2-. And then we're just going to crisscross our numbers here. I'm going to need 2 3+, and 3 2- to get me to a neutral compound. Okay, here's one for you to try out. This one has a polyatomic ion. See how well you do with it. Okay, hopefully you paused it and took a shot at it. So chromium 6 means we're going to have a 6+ charge there. And then carbonate is CO3 2-. Again, I like to put that in parentheses, put the 2- on the outside. Then we're going to crisscross our numbers. Cr2, CO3 6. You need to look at that 2 and that 6 and see if they can be reduced, and they certainly can. So our formula here is going to be chromium, or Cr CO3 3, and that'll be your final formula there. We've talked about many times, and perhaps you know before you came into this class, that a lot of elements have chemical symbols that are not directly related to their English names. Fe for iron, Au for gold. Those are, of course, because they were named based on other languages. A lot of them are based on Latin. Some of them are based on German. There are a bunch of different references for these names, but again, a lot of them do come from Latin. And so here's a list of some elements, metals, and their Latin equivalent names. Now, the thing about Latin is Latin changes meanings to words using prefixes and suffixes. And so these are the Latin names for the elements. There is a set of names to represent the valence states or the charges. So we know iron can form a 2+ and a 3+, and the Latin names for those are ferric and ferrous. Ferric does not mean 3+. Ferric means the higher charge. So notice you look right next to the, or right down below on the list, and you see the copper 1+ and 2+. The cupric is the 2+. I do not expect you to learn a bunch of Latin names. This is not the preferred system anymore, but you will still see this kind of stuff referenced in various texts that talk about chemistry. So for the sake of this chapter, I do want you to put in your brains these 4. You need to know ferric, ferrous, cupric, and cuprous. And let's see how those things are going to work out. So for instance, if I give you ferric sulfate, you have to know that that ic means 3+. And you'll have a periodic table in front of you. And so you just remember ic means the higher charge. When you look at iron on the periodic table, it says 2, 3. So we know that 3 has to be the ferric. The ferrous would be the 2+. So you just write the charge out. Sulfate, SO4 2-. We're going to crisscross our charges. I'm going to need 2 irons. I'm going to need 3 sulfates. Don't forget to put that sulfate in parentheses. Okay? Take a stab at one more. See if you can name this one with both the Roman numeral name and the Latin name. Okay, hopefully you took a shot at it. So we have copper and we have cyanide, Cn-. And so if we separate our charges out there, cyanide has a 1- charge. There are 2 cyanides, means the total negative charge is 2-. Total positive charge has to be 2+, and there's 1 copper, so it has to be carrying that 2+ charge. So we could call this copper 2 cyanide. The Latin name would be cupric cyanide. If I give you this formula and ask for the name, I don't care which one you use. What you do need to be able to do is look at cupric cyanide and know what that means. So you will have to be able to go from the name to the charge, but not necessarily the other way if you don't want to. And that kind of wraps up our naming of ionic and covalent compounds. The next video is going to look at naming acids, and that will conclude our naming and formula unit.